Greetings. I am the head researcher from Zeno University of Technology and Design.
I am researcher 2.
And I am researcher 3.
And I am researcher 4.
We are here to display the fruits of our labor.
A labor of love.
We work for those we love.
We protect those we love.
Our project aims to keep your eyes safe from electromagnetic radiation. We all spend a bit too much time on our mobile phones, don't we? But you see, that's really bad for your eyes. You see, your little phones emit electromagnetic radiation. The most common form is light. Around us, light. However, the vast majority of the other parts of the electromagnetic spectrum are invisible to the human eye. There are specific frequencies of the electromagnetic radiation spectrum, separated into two categories: ionizing and non-ionizing. Both can damage the eyes. Non-ionizing radiation simply heats up the tissues in our eyes. Ionizing radiations knocks the electrons off the tissues, altering them to a large degree. However, for the purposes of the scope of our project, we will only examine the effects of IR and UV in our eyes.
Our project examines how the exposure duration and irradiance dosage of ultraviolet and infrared electromagnetic radiation increase the odds of contracting eye conditions.
Exposure duration is how long someone is exposed. Irradiance dosage is how much UV and IR someone's eyes is exposed to.
To come to an appropriate conclusion, we have to set up some assumptions to properly restrict the problem to give us relevant results for our project. First, the only factor affecting the eye health is electromagnetic radiation. Exposure to radiation is only due to the spectrum constraint within IR wavelengths and UV wavelengths. Second, we do not distinguish between different types of UVs and their effects, or IRs and their different effects. Some may be worse for their eyes, but we are not separating them. Next, we assume that the distribution of exposure is shown in this graph. Next, the average irradiance is constant over time. There will be no significant variance from day to day. This is to account for potential spikes in IR and UV exposure, such as accidents due to occupational or lifestyle choices. Besides direct device usage, there will be a constant ambient exposure. These assumptions will help us scope our problem exactly into how a specific part of the electromagnetic spectrum affects our chances in contracting eye diseases. Now, what are our variables, head researcher, and how will we display the fruits of our labor?
Hush, Keaton. You only speak when you're instructed to.
Meow.
Now we shall introduce our model. Our independent variables are represented by D for duration of exposure in years, I for irradiance in watts per meter squared, and P for percentage of cataract development in percent. Interesting.
we also have, in the other graph, time of exposure, T, in years. Then we have logarithm, lifetime radiation exposure in joule per cm cube. And then the z-axis here, percentage of cataract developments. So from our results of our data, we can see that when there's a longer time of exposure, and there is a higher irradiance as well as lifetime radiation exposure, then there will be a higher percentage of cataract development. Bad.
Bad!
Bad.
Bad!
Our data validates each other, and it makes sure that our model is accurate and good, right for the picking.
Good work, kitten.
Very good, kitten, but I told you to only speak when you are instructed to.
Meow.
Wow.
So, why do we want to investigate this? By modeling a duration of exposure to the irradiance in watts per cm squared, we can determine the amount of energy density exposed to a person in his lifetime. By using this, we can see what's his percentage of getting cataracts and having other eye diseases such as cancer, which is bad.
Bad!
Bad.
Bad.
However, while we model this data on people with the occupational hazards of IR and UV, this data is important for other users, such as mapping to a general population. By using their duration of exposure to the irradiance of ambient light over time, we can determine whether they have a high percentage of developing cataracts over time.
However, our model does have some weaknesses. Firstly, our model may have insufficient data to reach a proper conclusion that is very representative of the general population, because much of our data was taken from a study done many decades ago. This data itself might also not be perfectly accurate because they are all estimations. This data also fails to calculate a best fit line equation in order to be extrapolated accurately because they are line points. In reality, the different types of ultraviolet and infrared and just radiation waves have different properties and may affect the eyes at different levels with different consequences. Also, the distribution of the light may not be representative of what happens in the daily life in this metropolis. We also do not account for genetics and medical conditions which could affect the probability of getting cataracts.
With our model's conclusion, we hence recommend future governments and leaders to take precautionary measures as well as preventive measures against the effects of direct and ambient electromagnetic light radiation on eye health. Thank you.
Meow, meow.
Meow.
Meow.